Today, we want to talk about quantum-safe cryptography. My name is Ulrich Kohn. I'm from ADVA's solution marketing team and joined today by Schlegel, our security expert within the PLM organization. There's a lot of talk about quantum computers and the threat they may create for presently applied security controls. There's this discussion about quantum-safe cryptography. So why do we need to make our networks quantum safe? Uli, could you please shed some light on this?
So the problem is that a lot of people are doing research on so-called quantum computers. That's IBM, that's Google, and that's a lot of others. And they have been quite successful building this kind of machines. So as of today, in a kind of smaller state, I'd say, but the idea behind a quantum computer is to break complex problems. So for example, if you have chemical problems, pharmaceutical things to calculate with a lot of input variables, you can really use that machines to really solve those problems in basically no time. Unfortunately, the same problem or algorithm problem applies to encryption, to what we use today in our HTTPS browser or whatsoever. So once those quantum computers in a bigger size will become available, you could, from a theory perspective, basically break our encryption, what we use today, nearly in no time.
You just made the statement, once those computers become available and become powerful enough, they will break. So does this mean we don't need to be concerned today?
Well, actually, most of the people believe that we will see big size quantum computers within the next 5 years with a probability of roughly 50%. So you never know. This could be tomorrow, this could be in 10 years, this could be never. The problem what we really have today is there's a lot of secrets, if you think on governmental stuff, for example, or researcher stuff, which need to remain secret for a very long time. So today, human mankind would have the possibility to grab huge data streams and just store it on disk. So they can sit for a while there, and once you have this quantum computer out, you can simply use that data stream you covered today in 2021 and decrypt it fully and easily in maybe 5 years from now.
Okay, so this means that equipment which we bring out into the field should even today be quantum safe. So now let's look at security controls. You made the point that with those powerful quantum computers, some parts of our security mechanisms might be vulnerable. Could you please explain which pieces are extremely vulnerable and need to be taken care of and considered?
So for the high-speed encryption, we and mostly everyone else uses the so-called symmetric encryption, which is based on the AES algorithms. We use today, or also most people, an AES size of 256 bit. That's still efficient, and that's still enough for even what we call post-quantum area security. The quantum computer might or will have the possibility to weaken that a little bit, but it's still enough and still good enough that those computers will not break the synchronous AES encryption. Whereas on the other side, for example, the key exchange is based on what we call asynchronous encryption. You might have heard about protocols like Diffie-Hellman, like RSA or elliptic curve cryptography. And exactly those ones are vulnerable to a quantum computer attack or a potential quantum computer attack. So we need to make those key exchange protocols sure, because they, of course, kind of exchange or establish the AES key we use later on. And once that's out, you can just read everything like clear text.
So this means the cipher we apply to secure our user data is quantum safe. That's not the problem. It's right. The key exchange protocol. So we need to have means which exchange those secrets in a secure way, secure that even a quantum computer cannot attack that.
Exactly.
What solutions do we have? What technologies can we apply here?
There is basically two ways we can do that as we see that today, or two technical feasible ways. One is around since maybe 5-6 years. It's what we call quantum key distribution. This is basically two separate optic electronic boxes who use physics to secure a key over a fiber, or to establish a key over a fiber. Once you have that done, then the key could not be eavesdropped anymore. The keys which are generated out of the boxes are, in theory, from a physical fundamental aspect, safe. Those keys will then be taken by our equipment and will be fed down towards our modules who do really the encryption work and being used as AES keys on the end of the day. So from a physical perspective, that's really rock solid, but there are a bunch of backdrafts. It's kind of not the time today to go deeply into that. The post-quantum cryptography is an algorithm-based security, which is also partly around since a couple of years. So a lot of people thought about that already, and the US NIST is currently working on setting new standards for the so-called post-quantum area. That's an algorithmic problem where people, I'd say, believe it could not be easily broken by the quantum computers. Since we don't have that machines, it's still kind of risky, but there is algorithms on the table which have been developed in the 80s and the 90s. A lot of people tried to break it and, of course, thought about it. And this is, from my perspective, a good way to go, because it's suitable not only for layer 1, also for layer 2, for layer 3, and even for IoT devices. You could use those algorithm-based post-quantum algorithms.
So this is two different possibilities you have to make your networks quantum safe with post-quantum cryptography and quantum key distribution. Recently, ADVA has launched a product with the FSP150XG118, and this already is prepared for those post-quantum algorithms, which can be uploaded onto those devices as NIST has concluded with the standardization. Ulrich, could you please comment, is there other solutions, preparations ADVA is taking with other products for this post-quantum age?
Yes, indeed. I mean, we made a lot of proof of concepts with this technology. And on the end of the day, we picked an algorithm which is called classic McAleese, which is, of course, in the finalists section of NIST. And it is also taken by the German BSI for post-quantum cryptography. And these algorithms will go in one of our FSP 3009 modules, and the combination of the PQC with BSI approval will be released within roughly September timeframe. And so I think we will be the first people on Earth having a real productized and approved version of post-quantum cryptography on a commercial available product.
Excellent. Thanks a lot for these explanations. Thanks for the insight you shared with us on quantum safe cryptography, highlighting what is the issue, what is the problem with presently applied security controls, and how these challenges can be mitigated with what you explained, post-quantum cryptography and with a quantum key distribution. It's good to see that ADVA already has launched products prepared for the post-quantum age and is releasing pretty soon the first optical transmission system with a quantum safe technology. With this, I would like to thank Uli for participating, for sharing his insights with us, and thank you to you, our audience, for visiting to our TechCam video. Thanks a lot.
TechCam.